Hey class, how's it going? We got our kind of first example questions of our work and energy. So I'm going to be doing question 2 and 3 from the practice sheet, as well as I'm adding I'm going to call them like kind of flip questions, where they're similar to questions 2 and 3, but I'm going to kind of word the questions or kind of give the questions and then answer that new question, because I wanted to give some more questions than just this. I couldn't find very good ones that I really wanted to get out to you guys for the practice sheet, but I'm going to add them into this actual video here. So we're actually going to have 4 questions, question 2 and 3 from the practice sheet, and then I'm going to add kind of my own little ones as well here. So let's go through this. Let's look at, there we go. So let's actually make this a little bigger. And so here's our first question, question 2. So it says, how much work is required to lift a 4 kilogram mass up a distance of 2 meters? Now, if you look over here, I've added my 2 other formulas. I have my work equals force times distance, and work is also the change in energy, change in kinetic energy or change in potential energy. I also have my potential and kinetic energy here. So here's the 4 formulas that I'm probably going to be using kind of a little bit today. Now, again, a lot of people here will just want to use this first one, force multiplied by distance. They're like, oh, I got a distance, I'll multiply by this and we're all good. This is not a force. This is a mass, okay? Now, there are still 2 kind of ways that we can do this. They end up being exactly the same though. If you want to try and find the force to lift a mass, again, if I want to lift up this box, how much do I need to lift? Well, force, again, is just mass times acceleration, so 4 times 9.8. So I think that'll give you like 39.2. 39.2 will be the force that you need. And now if you go 39.2 multiplied by the 2, you'll get your answer. So let's do that. Work equals my force, 39.2 multiplied by 2. And I get an answer of 78.4. 78.4 joules. So that's the way to use this part of the formula. You could also use this one though. What is the change of energy? If I'm going to get it to a distance of 2 meters, I've changed the potential energy. So let's actually look at it that way. Well, I had 0 potential energy on the ground, and now it's at 2 meters, so it has potential energy. What is that change in energy? Well, the change of energy will be the potential energy. So mass times gravity times height, which is 2 times 9.8 times 2. Okay, and so if mass is 4. Whoops. Mass is 4 times 9.8 times 2. And when I get this, I also get 78.4. And you notice that in this potential energy, I literally did mass times 9.8, which is exactly what I did over here when I found the force. Okay, and so they both give you 78.4 joules. Okay, so both ways work here, and either one is fine. If you want to find the force it takes, fine. If you just want to look at the change of energy, also fine in this question. All right, let's go to a kind of a flip question. A question that's similar to this one, but just a little different. Okay, question 2, flip. If there is a 25 kilogram box, and 300, so I'm giving you the joules, I'm giving you the energy or the work, however you want to think about it, okay? Energy used, work used, 350 joules are used to lift the box up. How high did it move? I need to know the height, okay? I need to know kind of the distance that it moved in the up direction. Now, usually, most students, when they see the word like lift up high, they automatically go with potential energy, which is fine. It totally works, and honestly, it's probably the best way to go. Because as soon as you have like how high did it move, that potential energy is usually the easiest way to go. And let's kind of think about this. If, again, I need to, this is, again, how much energy was used. So in the end, that's how much potential energy it should have. We don't have any friction yet. We don't have any like loss of energy. So if I use this much energy, that's how much potential energy I have at the end. So my potential energy needs to equal 350, which means 350 needs to equal mass of 25 times gravity times my height. And so when I divide this by 25, divide by 25, I think I get 12 equals 9.8 times height, divide by 9.8, divide by 9.8. I think I get a height of 1.4 meters. 1.4 meters. All right, so that's how to kind of look at this question. That's similar to the other one, but it's just a little flip. But here, yeah, again, when you have the energy that is work, it's also the change energy. If I'm starting from the ground and I'm lifting up, all that energy used has to equal the potential energy at the top, kind of like our conservation law. So that kind of works into here. So there's how to kind of get the height off of work here. Oh yeah, cool. Let's go to question 3 from our practice sheet. Question 3 from our practice sheet. All right, so it says an 80 kilogram box is pushed 4 meters. So mass equals 80 kilograms. It moves a distance of 4 meters. Okay? It says 4 meters across a horizontal surface by 45 newtons applied. So the force was 45 newtons. Cool. A, it says how much work was done. Okay, well this one's pretty easy. I'm giving the force, I'm giving the distance that it goes. So the nice thing is work's pretty easy. I don't have to worry about the change of energy just yet. This is pretty easy. So all I'm going to do is just go 45 newtons times the 4 meters, and I get 180 joules. 180 joules. So 180 joules was used to move this box. Oh yeah. It says if the box started from rest, what is the final speed? Well, now I'm talking about it has some kinetic energy. I've put a bunch of work into this. Obviously, when I'm moving the box, it's moving, it has some kind of velocity, so it has some kind of kinetic energy. So we're saying that again, if I'm pushing this box, there's no friction yet. So all this energy has to basically be used into some kind of actual kinetic energy. So let's actually think about that. If I have, again, my total energy, my energy is 180 joules. What's the kinetic energy? Well, I've converted this from rest to a kinetic energy. So kinetic energy is going to equal 180, which means 180 joules is going to equal 1/2 mv squared. I know my mass. I'll put my mass at 80 in there. And so let's figure this out. Well, 1 second. Got a little dark. There we go. Okay. So if I do this, so that makes it 360. 360 divided by 80 gives me something. Where's my calculator? Let's do this quickly here. 360 divided by 80. So I get 4.5 equals v squared. And if I square root 4.5, I get 2.1. My velocity will be 2.1 meters per second. So basically, when I use this much actual force, I was able to then create this velocity of 2.1 by moving this box. Cool. All right, and if I really want to get fancy and add kinematics in here, now that you know the velocity final and you knew the velocity initial, you can actually figure out what's the acceleration. But I won't throw that in there just yet. We'll ignore kind of kinematics for week 1 here. All right, let's do one more little new question, and then we'll be done for this video. So this one's not on your practice sheet, but I kind of alluded it into like the intro video, and I kind of just want to do one more similar one here. And so So it says if Mr. Westwood was running down the street at 3.5 meters per second, so I have initial velocity, VI of 3.5 meters per second. Okay, suddenly saw a mini donut truck. Okay, I love mini donuts, they're good. Who can resist mini donuts? He changed the speed to 8 meters per second, so velocity final equals 8 meters per second. What was the work done to change the speed if the mass is 80 kilograms? Mass is 80 kilograms. Might be more after those mini donuts, but we'll leave it at 80 kilograms. So this would be hard to find the force and distance. You could figure it out. Like you have the VI and you have the velocity final. I don't give you a time though, so it's going to be hard to find that distance. Let's just go right to our change of energy, okay? Because we can do our change of energy pretty easy. What is our kinetic energy at the start? Kinetic energy at the start equals 1/2 times 80 times 3.5 squared. Okay, so let's do that. We have 3.5 times 3.5, okay, times 80. So I get 490 joules right here. Let's find my kinetic energy at the end. I'm going to go 8 times 8 times 80, a lot of 8s, by 2. I'm much bigger. So 1/2 times 80 times 8 squared. This gives me 2,560. So what is my change in energy? What is my change in energy? You're just going to minus those. This is what I started with. This is what I ended with. So if I go with that, like 2,560 minus 490, I get 2,070. That is my change in energy, which means that is also the work done. So work is also 2,070. Okay? So there's a few examples of how to kind of find work using a couple different ways, either our change of energy or just our force and distance, and kind of how I go about thinking about how to answer these questions. So there's kind of our first worksheet, or our first part, not worksheet, first part of this. There'll be one more video talking about question 5 from our practice sheet, as well as 2 other questions that I've kind of wanted to touch on. All right, cool. Let's get rid of this for a second. And then go here. All right, class, thanks so much for watching. Have a good day.